Okay, so prove that cubic equations must have at least one real root. So consider a, b, c, d, which are real, and a is not 0. Let k equal 1 plus the maximum of absolute 3b over a, square root absolute 3c over a, and then cube root absolute 3d over a. Now, because of the design here of k, and also let f of x equals x cubed plus b over ax squared plus c over a x plus d. Because of how I constructed the k, it would mean that f of k, which by the way is positive, that would end up being positive. What will happen is that this piece here will be bigger in size, more positive than whatever this could be potentially as a negative number. So let's suppose, for example, b, c, and d are all negative. In terms of size, this will be bigger than these three combined because of my construction of k with the 3 in the numerator, and you're picking the biggest one out here and adding 1. And likewise, f of minus k will be negative. So the intermediate value theorem would imply that there exists an x in the interval minus k to k such that f of x could equal 0. That would mean then that, x cubed plus b over a, x squared plus c over a, x plus d could equal 0. So that would mean then that ax cubed plus bx squared plus cx plus d could equal 0, i.e. There exists one real root. And not only have I shown that there's one real root, I've even provided a range to search out for the one real root. So, for example, I did a calculation earlier. For example, e.g., if a equals 4, b equals 3, c equals 2, and d equals 1, oh, I deleted it. I think I got something like k will equal 3.25. So there's a root between minus 3.25 and 3.25, and it was something like somewhere near 0.5. I don't remember. You can calculate this for yourself. So I like this proof because it puts, not only does it prove that there's a root, but it also puts boundaries on where the root could be. So like there's minus k, there's k. You know that there must be at least one real root between these two.